Hello, good morning to Anda. In the previous videos, we have seen the course Signals and Systems, first, second, and the third units. And this is the fourth unit of the course Signals and Systems. Myself, C.H. Amanna Sarma, faculty from ECE department. Okay, from PBI Resource Engineering College, PBI WITS Havel. Okay, and in this fourth unit, the title is Signal Transmission through Linear Systems. So here we will start the chapter by defining systems, as we already defined the systems classification system in the first unit. So we have just to take a brief lecture on system, and then what happens if the signal is transmitting through the system, how the signal has to be analyzed, and what is the effect of system on the signal will be how that effect will be estimated is going to discuss in this unit. Okay, so let's start. The system is defined as a physical device that generates some response by taking inputs. Okay, the response is also known as output, and the input is also known as excitation. Examples are amplifiers, filters, as I taken in the first unit, television set, tube light, fan, whatever thing, including the education system. College is also a system. Okay, so amplifier will take low frequency, low amplitude signal and boost them up and amplifies this as output. Filter, only certain part of the entire signal, entire thing is translated, that is filter. So these are all the systems. So a system can be represented by using block, by input with inputs and outputs. A system is mathematically defined as y of t is output, x of t is input. Y of t is equal to t of x of t, where t is transformation. Some operation has been performed on x of t, which has given as an output y of t. So this is the block diagram of a system. System inputs are excitation, outputs are response of the system. So system is having output response and impulse response. System is defined by its impulse response. System output is identified by the input impulse. That will be discussed in the coming sessions. Okay. So the system mathematical equation is y of t is equal to transformation of x of t, t of x of t, and this is the block diagram of a system. Linear and non-linear system. The system is said to be linear if it obeys the principle of superposition. Okay. So superposition theorem is sum of the responses is equal to individual responses. Like that you will get the systems. Already we have discussed about the linear systems and non-linear systems in the first unit. So superposition principle states that the response of a weighted sum of input signals must be equal to the corresponding weighted sum of outputs of the system. So this is called as, that is, a x1 of t, x2 of the inputs, and a is the scaled, that is the scaled inputs. Transformation of, if you combinedly apply as an input, the output is equal to individual sums. So like that the system must be, that is called linear system. X of t is using, so it is a continuous time. If you are using x of n, it is discrete time system. Transformation of a x1 of n plus b x2 of n must be equal to a transformation of x1 of n plus b transformation of x2 of n. This is known as linear system. If this condition does not satisfy, then the system is known as non-linear system. Systems are generally linear in nature. Similarly, time variant and time invariant system. If the system response does not vary with respect to time, that is known as time invariant system. System must be time invariant in nature. If the system varies with respect to time, that is time variant. Suppose if any system is temperature dependent. For example, if you take a diode changes its cut-in voltage, the voltage levels based on the temperature. That is in that we are already having one equation IC. In transfer having the IC, a reverse saturation current, that will be changed by increasing the temperature of the room temperature or the working temperature of the device. So that diode or the semiconductor devices, whatever it may be, diode, triode, transistor, pentode, FET, whatever it may, all these are all non-linear devices, and they are time varying devices or time varying systems. If the system does not vary with respect to time, for example, if you take RLC, they will not change their values with temperatures. Such systems are known as time invariant systems. So that usually system must be time invariant and it should be linear. So mathematically it is defined as y of t minus capital T. Capital T is delay in time, not transformation here. So if there is a delay in the input, the same delay must be reflected in the output. So such systems are known as time invariant. If that delay is not reflected, that becomes time variant. So this is the example of time invariant system. Input is given, output. So there is a output, input, almost both are same because this happens in a practical scenario, but theoretically it is whatever is input, that is say input is u of t function, output also u of t function. So this is transmission error. It is called transmission error or raise time error. It will be happens in any invariant system. Similarly, delayed time input, the same delay is reflects in the output. Okay, like that the time varying systems are defined. Okay, a system which obeys both linearity principle and time invariant principle, that is known as LTI system. An LTI system is most important system. When if a system is LTI system, it is the best system. System obeys both principle, that is LTI systems. Response of a continuous time LTI system. How you will calculate the response? So the response is generally impulse response. It is noted by h of t. So it's any LTI system can be defined by its impulse response h of t. H of t is equal to transformation of del of t. Impulse function. If input is impulse function, then the response of system is impulse response h of t. Delta function which is defined at t equal to 0. So if you apply a delta function as an input to the system, then the output of the system is actual behavior of that system. That is called impulse response, and that is ideal response. Ideally, the response of the system. Okay. The response of for the system is if input is any other than the del of t, then the system response is known as actual output or response of the system. And that is defined for this one, the x of t is equal to integral minus infinity plus infinity x of tau into del of t minus tau. So if you apply input and to this system, then output is also scaled by the same distance tau. Okay. Next, y of t is equal to transformation of x of t. What is x of t? Integral minus infinity plus infinity x of tau into del of t minus tau d tau. Then minus infinity, so transformation operation can take into the inside of this particular thing, then the transformation of del of t. This is called h of t. This transformation tool is represented as h of t. H of t already given. H of t is transformation of h of t already defined. H of t is equal to transformation of del of t function. So del of t minus tau, so it is h of t minus tau. Then y of t, output of system, is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. So this is the actual output or response of system. Del of t, h of t is known as impulse response. Impulse response is when the input is delta of t, then the output of the system is known as impulse response. That impulse response is used to analyze the actual response of the system. If you apply any arbitrary input called x of t, then y of t is equal to the same transformation tool operates on x of t. But actual x of t is defined as x of tau into del of t minus tau d tau. So substituting that function, then you will get y of t is equal to integral minus infinity to plus infinity x of tau h of t minus tau d tau. This is summation. It is nothing but the convolution sum formula. So one can say by seeing this expression that LTI system output is x of t convoluting with its impulse response, that is actual output of the system. So convolution sum is x of tau integral minus infinity to plus infinity x of tau h of t minus tau. This integral is known as convolution sum integral and it is united by x of t convoluting with h of t. Therefore, the output of LTI system or response of LTI system h of y of t is equal to convolution of input function with its impulse response. So output of any LTI system is convolution of input signal x of t with its impulse response h of t. And mathematically, if you want to estimate the output of an LTI system, you have to solve this integral. So to solve this integral, we need to know what is the impulse response. The impulse response will be obtained by giving delta of t as an input. So this is how a response of an LTI system will be. So for simplification, y of t, if you take Fourier transform or Laplace transform or jet transform for this signal, if you take Fourier transform, it becomes y of omega is equal to Fourier transform of x of t convoluting with h of t. So convolution of Fourier transform, convolution property is there. Convolution in time domain results multiplication in its frequency domain. So y of omega is equal to x of omega into h of omega. Like that, you will directly estimate the spectral components of the h of t also. From that, you also identify the spectral component of the impulse function. Then h of omega is known as transfer function. Impulse response is time domain. H of omega is transfer function in its frequency domain. Okay. So now this formula or this equation is block diagrammatically represented like this. LTI system is input. If delta of t is input, see above this arrow is delta of t, above this arrow is h of t. If delta of t is input, h of t is output. If you replace x of t, if x of t is input, h of t is equal to x of t convoluting with impulse response h of t. So this is the block diagrammatic representation of an LTI system. Coming to the here, I just outlined main important properties of a convolution. So if you know these properties, if there are multiple systems in a block, so you can easily solve the output of the response of the system. So this is practically, this scenario is used when in any system if there are interconnected with multiple systems. For example, if you take a weather forecasting system, in that temperature sensor will be there, humidity sensor will be there, and also pressure sensor will be there. All these sensors should interconnect, and they work together to identify or to forecast the weather conditions. Similarly, if there are these three systems and they are interconnected, so such problems can be solved by understanding the properties of this convolution integral or system. Directly we are giving the properties of output responses. Okay, for example, the convolution sum satisfies the cumulative property, that is x of t convoluting with h of t is equal to h of t convoluting with x of t. So that is, it satisfies the cumulative property. And second, it satisfies the associative property. If there are multiple systems, so there suppose multiple x of t, x of h of tau, h of t convoluting h of t. So you can multiple that is a convoluting b convoluting c is equal to a convoluting b convoluting c. That is associative property. And then the distributive property, x of t. If there are two systems, so you can add x of t convoluting with h of t plus h2 of t, then it is also equal to x of t convoluting with h of t plus x of t convoluting with h2 of t. So a convolution integral satisfies these three properties. So a system also satisfies these properties. So either you can input to system or input to system or input from system, you can define. So like this, these are all the three properties of a convolution. So our systems also satisfies these properties. Thank you. In the next lecture we will see some more topics on this unit. Thank you.